There's actually only 3 up here because 2 of these are the same. Which 2 are the same? 2 and 4? Did we say that? Yeah. These are the same. We're going to call this a meso compound. So actually, I'm going to mark that out and call this 2. Okay? Because that's really just compound 2 redrawn.
Sorry, are 1 and 3 not the same?
So 1 and 3 are not the same.
They're not superimposable, right?
Okay? 1 and 3 are not. What's the relationship between 1 and 3? Since I'm telling you they're not the same,
Oh,
what's the
that's right,
relationship? 1 and 3 are enantiomers because everything's reversed. If 1 looks in the mirror, what does it see? Everything's reversed. It's like 1 has 2 right hands. And if you look in the mirror, your mirror image is going to have 2 left hands. Okay? 1 and 3. The question is the mirror image different? And in 1 and 3, they are different. But how do we know that? Now, 2 and 4, those are actually mirror images. But is mirror images always different? No, the 2 paper clips. The mirror image is the same thing. So how do we know this? Ultimately, how do we determine plane symmetry? So, thus, 1 and 3 must not have a plane of symmetry. Compound 1 must not have a plane of symmetry if I'm telling you it's an enantiomer. But compound 2, does compound 2 have a plane of symmetry? It must if I'm telling you that what looks like the mirror image is the same thing. We've got to find planes of symmetry. The best way to find planes of symmetry is to draw things in Fisher projection. First off, you've got to be able to do that anyway. But once you do it, it's easier to see planes of symmetry. Let's draw compound 1 in a Fisher projection. Now, you could have cheated, because we kind of did this with the OH and the chlorine before or something. Okay? But I'm going to do it fresh here. This is compound 1 Fisher. I got 2 chiral carbons. I've got methyls on the end. I'm going to draw those in. I'm going to call this methyl 1 and this methyl 4. 1, 2, 3, and 4. I'm going to put methyl 1 at the top, methyl 4 at the bottom, alkyls at top and bottom. Since methyl 4 is at the bottom, the ground is here. 4. Now I can stand on the ground. I can look at this chiral carbon with the methyl going away. Because if I'm looking at this, that's going away. What that means. Up is going away. So I want to look at it with the methyl going away, so I need to stand over here and look through there. Pretend I'm up a little bit and looking through there. So I'm looking with methyl going away, and the OH is towards you, because it's bold. What side is it on as I'm looking there? The OH is on my left. I just want to draw this. Here, this is what I'm drawing, okay? Methyl going away, OH on the left. That's what I'm seeing. What else is on this carbon? H going to the Hall. So if it's going to the Hall, it's on which side?
Right.
Hold on, they can't both be on the left. Hold on, I'm supposed to be looking over from over here, right? And if the H goes to the Hall, it's my right. Okay. It's on the right. Now let's look at this carbon. Methyl's going away. If I'm looking through here, uh-oh, methyl's not going away. It's coming towards me. See how it's coming towards me? So I need to do what? Your book may say rotate something. I say no. I say come over here and look at it this way. And now keep your feet on the ground because in a little while you'll have your feet in the air. Don't do that. Okay? Look through here. The methyl going away, and this thing coming off the board towards you, and I'm looking at the methyl going away. This OH is on my right. The H is the other way, it's over here. There it is. This is compound 1 in a Fisher projection. Okay? Do you see the plane of symmetry? This can be difficult to see planes of symmetry. It's easier to see here because the methyls are both going back. So the methyls are mirroring each other. If we come through here, but is that a plane of symmetry? This is where we're going to look for planes of symmetry in fissures. Methyl going back, mirroring methyl going back. OH going forward, not mirrored in OH going forward. There's no plane of symmetry here. Okay? I don't see one. Trust me, you would see it in the fissure. Now, if you want to do a model, let's do the model, and then let's look for the plane of symmetry. Let's start here. Methyl. There it is, zig, zig, zig. The OH is going forward. See, I got the wrong orientation. I got the wrong. OH going forward. I got the wrong here also. And see, look, with the backbones zig, 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 there's no way to make the OH forward. I mean, I can make it forward by doing this. Now it's forward. But the methyl is no longer straight up in the plane. The methyl's not going back. So you can't just rotate. The only way to get that OH forward, the methyl up, is to disconnect and do a different orientation. And when I do that, I'm going from R to S. Everybody see that is this compound on the board? Both OHs coming out. And the little things going back, those are the H's. Okay? Now, we just drew this on the board with this center carbon vertical. Look at the bottom. With the methyl going back, that's what that means. Right? Which side's the OH on? See it's on the right? And over here, that's your right, correct? And to your left is the H. That's what we got here. Ah, but hold on, top. The OH is to the right. But is the methyl going away? See up here, we just rotate. Now with both methyls going back, the lower OH is on the right, the top OH is to the left. So that's how this is drawn. But we got there from looking at it as I showed. Now that we got it, this is it. Now we can search for planes of symmetry just here. I could slice right through there and I cut right through the methyl, the 4 carbons. If I slice right through there, is that a plane? No. OH on one side. Okay. Well, what if I turn this like this? What if I slice through the OHs? Is that a plane of symmetry? No, I got a methyl over here and a methyl over there. Well, what if I slice right through here? Methyl on one. You're never going to find a plane of symmetry. Anybody find one? So there's no plane of symmetry. So what does that tell us about the mirror image? It's going to be different. No plane of symmetry, mirror image is different. What is the mirror image going to look like? Well, if this is RR, the mirror image would be SS. Well, this one is actually what? Did we determine these two? Well, these are RR. So the mirror image, when you look in the mirror, what do you see? We just know that. It's SS. But is it the same compound or different?
Different.
It's different because there's no plane of symmetry. It's going to be different. Let's build the other one and make sure they're different. There's that one. Pretty sure this is the other one. Zigzag. Boom, boom, boom. There's back. Playing the board. This OH going back. You see how it's going back? That OH coming. Hold on. Oh, we need this one going back also. So this is not. With the zigzags on the plane of the board, both OHs going back. If I Everybody see that? If you ever can't see, say, hey, I can't see over here. So, that's the mirror image based on RR turning being SS in the mirror. Well, let's see if their mirror image is holding here. Let's see. I'm going to do the methyls this way. If that looks in the mirror, what does it see? It's going to see methyls going away from it. Here we go. If that looks in the mirror, does it see that? Do those look like mirror images? Hopefully they do. See how the OH is that way of mirroring? Yeah. See their mirror images? Everything has a mirror image. The question is it the same or not? We've already answered it because we could not find a plane of symmetry, so that means that the mirror image is not the same. But if it's not the same, let's see if it'll stack on each other. Look, all the blacks line up. So they're stacking. Are the reds stacking? No. They're not. And they never will. These are two different molecules. What do we call these two? Enantiomers. They're mirror images that are not the same. What else do you want to call these compounds? A pair of what? It's a DL pair because one rotates light one way and the other rotates light the other way. I don't know which is which. It's a DL pair. Okay. So it's said. Now let's look at 2 and 4. Or, as I've already told you, it's really 2. It's the same thing. First thing, let's draw 2 in a fissure. Well, you can't cheat because the only difference between 1 and 2 I'm going to draw it up here. 1 and 2. This is R, and this is S. See, that carbon hasn't changed. If we call that methyl 1, methyl 4, methyl 1, methyl 4, the top carbon hasn't changed, so it's over here. But this carbon has changed, so the OH should be where? It's going to be on the left. Let's prove that. Let's look at this. With the methyl going away, so I stand over here, feet on the ground because carbon 4 is closer to the ground. With methyl 4 going away, is the OH on my right or left? Well, it's going to the Hall, so if I'm looking that way, the Hall's on my left. So it's like this. So this is this. And the H is here. And when we draw it in a fissure, what do you see? You see symmetry. Where do you see it at? Right there. See the plane of symmetry? It's so much easier to see in the fissure. Since you see a plane of symmetry, what do we say about the mirror image? First off, is this the mirror image?
Yes.
Yes, because this is S and this is R. Everything has a mirror image, and the mirror image is always switched. But is it different? No, it's not. It's not any different. Because it has a plane of symmetry. Let's do the same thing as we did before. I think we need to go, I think I need to switch here. This should be this one. With both methyls going away, both OHs are on this side. Is that one? Now let's do the other one. We didn't do that. Let's draw that in a fissure. We didn't do that in a fissure. Let's do it from scratch. Methyl 1, methyl 4. With methyl 1 going away, is the OH, that's 1 and this is 4. 4 is closer to the ground. With methyl 1 going away, is the OH here on my left or right? On my right. Thus the H on that carbon is over here. Okay, here. Is this OH on my left or right? I gotta look at it with the methyl going away. Right now it's coming towards me. I'm standing over here. I gotta come over here. The methyl going away, this is coming out towards you on the right. Okay, look at these two. If this is a mirror, do those look like they're mirroring each other? Indeed they are. They're mirror images. Same or different? There's that one. OH is this side. Here's this one. You didn't see that. OH is that side. Methyl's going back. Same or different? Well, look. Look. They all just stacked on this. They just stacked on each other. It's the same compound. You see it? Can you tell the difference in the two? Same compound. The mirror images are the same. Well, we know that because if we find the plane of symmetry, the mirror images will be the same thing. Fisher helps you find the plane of symmetry. So what do you call 2 and 4? You call it the same thing, so they're both 2, really. What do you call a compound that has chiral carbons? Because it does have chiral carbons, yet the compound as a whole is not chiral. The mirror image is the same thing. Meso. You call that meso. This is a meso compound. There's really only 3 compounds on the board. 1, 2, and 3. 4 is just a repeat of 2, just drawn and flipped over. Questions about this? You have a DL pair. What's DL pair? 1 and 3 is a DL pair. And then you got 2, which is a meso compound. One and 3 are enantiomers. What's the relationship between 1 and 2? Diastereomers, because the RR versus RS, that's diastereomer. Diastereomers have totally different properties. It can be very close, but it also can be very different. Okay, let's look at the sheet here. I think we did these 3. I think I want you to do the rest of these on your own. We'll look at them tomorrow. Basically, you're looking for plane of symmetry. If you can find one, then it's not a chiral compound. Does that have a plane of symmetry? I'd recommend drawing it in a Fisher projection. Then the planes are much easier to see. Let's do one up here, though. This individual one up here. Let's do that here. Show a Fisher projection with fill in top and bottom, and then tell me, is it erythro or trio? Right here. Do that right now. I should have told you a little trick before I erased up here. So let's look at this real quick. That was SR. The first one was RR. be looking for plane of symmetry. Well, first off, why was there no plane of symmetry when that was a chlorine? Well, when it's a chlorine, you can't divide it in half and have a OH mirroring an OH. So you got to have some intuitive, like, there's potential for mirroring for a plane, okay? You got to have one, this half of the molecule being the same as that half, at least. But then you have to have the right configuration to mirror. So this is not going to be a plane here. When this is OH, it's potentially, because on this side of the plane, you've got a carbon, you've got the same atoms. How do we know that this is not going to be a mirrored plane, though? Here's the trick. Free information. If I'm saying this is a plane of symmetry, that basically means it's an internal mirror. Are these sides mirroring each other? Why not, Sarah?
Because of both RR and the mirror.
Because what's the mirror of R?
S.
S. See, that's a trick. It's not going to be a plane of symmetry. Indeed, when we did it, we couldn't find one. But look over here. Over here, you've got the same things on both sides. And on one side you have S, on the other side you have R. What's the mirror of S? See, this is potential, okay? That's a little trick to kind of keep in mind. A meso is always going to have, like, RS. It's never going to be RR. Because that would not be an internal mirror plane. Now, you can also have multiple. You can have SS and RR. You can have 4, and one side mirror the other. Okay? All we're doing is just 2. And a little bit later, I'll show you some with 6. It'll be very sweet. All right? Okay, draw that in the Fisher. Tell me if it's a erythro or a trio. Remember what those two terms mean? With phenyl at top, phenyl's a benzene ring, ethyl at bottom. Those are your 2 chiral carbons. I got 2 chiral carbons, so I'm going to do 2 crosshairs. And it says put the phenyl at the top and the ethyl at the bottom. Well, that's not chiral, but that can still be an ethyl coming off of that chiral carbon. So from there, I want to put the fluorine and the chlorine. Each chiral carbon has a halogen and an H. Anybody got the erythro trio? Barbara? Trio. So your priority groups, which are your 2 halogens. Your halogens are on opposite sides in your Fisher. Yep? Okay, let's see. Anybody get erythro? You got erythros? So erythro means everything's on the same side. So erythro is your 2 halogens are on the same side in your Fisher?
Yes.
Which phenyl at the top and ethyl at the bottom?
Yes. Because you can rotate.
Okay, well, let's do it. Let's do it. Phenyl at top and ethyl at bottom. So is the ground over here or here?
Left.
Ground's over here. The ethyl's closer to the ground. See the ground's right there. The ethyl's closer to the ground. Phenyl's in the air if it's at the top. So the ethyl's closer to the ground. So I'm standing on the ground. I want to look at this carbon. Let's see. How can I look at this with the phenyl going away from me? Because that's what that means, phenyl going away. I got a little problem here because the phenyl's not in the plane. If I stand over here on the ground and look through there, What's going away from me? Chlorine's going away. With the chlorine going away, what side's the phenyl on? Pretend I'm up there hovering.
Right.
Feet are on the ground, hovering up there. Chlorine's going away, the phenyl's coming out towards you, bold, so it's on my... This is what I'm going to do first. With the chlorine going away, phenyl's on the right. You see, just because I was told to draw it like this at the end, doesn't mean I have to draw it like that to start with. So that's what I'm showing you here. Now the H here is going back. So if I'm looking through there, the chlorine's going away. Which side am I the H on?
Left.
All right. Now do this carbon. Okay. With the alpha going away, if I'm here,
You're upside down.
I'm upside down. I'm upside down.
That should look like you're laying on this ground.
Should you be on this?
I need to keep my feet on the ground. Where's the
Because your
ground?
back needs to be toward the floor.
If I'm laying here looking away, my feet are in the air because the ground's this way. I need to be this way. Feet on the ground. There's the ground. Okay? I need to be looking with the feet on the ground through here. Pretend I'm laying here, okay? Feet on the ground. This alpha, the whole thing, just that bond is going away. With that bond going away, the F is on my left. With the alpha going away, the F is on my left. And thus the H is going to the Hall, is on the right. There's the compound in the fissure. How can we check ourselves? You can always check yourself by doing RS. Let's do that right here. This is RS over here. It is chiral. The H is going back. That's good. Which is high priority? Chlorine, that's a benzene ring with a carbon to a carbon. It's all carbon. Chlorine's 1, carbon with F is 2, carbon bonded to other carbons is 3. What is this?
R.
R. Is it R here? It better be. It should be the same thing. Chlorine 1, carbon with F2, carbon with all carbons is 3. That's counterclockwise.
The H is
But
But the H is coming forward, so it becomes, what is this?
R.
See? Same thing. It's either going to be RS. It should be R because that's what we're drawing. And the other one is right too. There it is. But we were asked to draw the phenyl at the top and bottom. Phenyl at the top, ethyl at the bottom. What can we do here?
rotating.
This can be just rotated, not disconnected. The top 3 can just be rotated there. Let me show you how you rotate it. Chlorine green going away. Phenyl is black. We'll call it black. Ethyl black going away. Chlorine red. Okay? This bond here I'm going to just hold and not spin. Okay? The top 3 can just spin any way you want. Now it's spinning, but as it spins, things just turn. The chlorine's going away. Now on the board I'll do it like this. Chlorine going away. Let's make the phenyl go away, because that's how we want to draw it. The phenyl going away, what side's the chlorine on?
Left.
Now over here. Okay? Basically, I'll put the phenyl up here. This can rotate either way. And if I rotate it, we're not going to change the bottom. F on the bottom here. The phenyl rotates up. Where does the chlorine go? Over here. The H swings over here. And it's still R. All we did was rotate. You can check that. Now we have it in the Fisher, and the answer is what, Barbara? Erythro. Because the high priority groups are on the same side. Sounds like Z. That's the same side, but that's alkene stuff. It's erythro-trio. Okay? Erythro and trio are diastereomers. Because if the CL was here and the F was over here, it would be like, this may be RR and the other would be RS. Okay, let's look at a couple miscellaneous things, but are very important. There's questions here. Please do these. There's no answer supplied. You can ask me, or you can just struggle with them. And okay, this is the example questions. Let's do one here. Similar to the one on the quiz, these are called fluoroquinolones, antibiotics. This drug here is levofloxacin hemihydrate. Hemi means half. Each molecule is associated with a half a mole of water. For every mole of molecules, kind of half a mole of water. Hemihydrate, the formula. That adds the molecular weight. Called levofloxacin, brand name Levaquin. Anybody know Levaquin? Okay. Question, is it R or S? Since I didn't clarify, it seems like it only has one chiral carbon. Well, indeed it does, and it's right here, and you can tell. Because in this structure, the stereo view is shown, so you're kind of quick to see that. By the way, what if this was shown like that? CH3, CH3, bold and dashed. It wouldn't be chiral. But I've seen a lot of students think it's chiral just because I showed the bold and dashed here. I could have showed the bold and dashed there. It is tetrahedral. But this is chiral because we have 4 different things attached. H, methyl, nitrogen, and CO. R, S.
S.
Nitrogen is 1. Carbon with O is 2. Carbon with H's is 3. Counterclockwise, H in the back, S. Yeah. When this drug is given, it's only S. Is it D or L? Is it D or L?
Do you need the number?
Well, D and L has nothing to do with R and S. I don't know.
You need the experimental number.
You have to see what the experimenter got. Is rotate like one way or other. But actually, you can tell. Look at the name. What's the name of this drug?
Is that
What's the name of this drug? Levofloxacin. Why do you think they call it levofloxacin?
Go to the left.
Because it's levorotatory. Okay? All right. A lot of times names come from chemical information. And I guarantee you it rotates left. That's why they call it levofloxacin. Question?
Would you ever ask us to do the IPAC name for that?
No.
Bless you.
I teach a class in heterocyclic chemistry, and you could, that's a quinoline. The fact that you got this third ring makes it quite difficult even for that. No. Okay. There's some others over here. You can determine R and S for practice. Those are given as individual enantiomers. These drugs over here are given as racemic mixtures. So if you, like albuterol, used for like asthma. Okay? Is here, given as a mixture of enantiomers. Where's the chirocarbon? Or there's at least one. Right there? Well, the drug that you take is both R and S there. 50-50 mix, racemic mixture. Some drugs are like that. Aleve, naproxen should not be like that. You're not going to be doing that in lab, right? Aleve should be one, but the other one's toxic. Okay, I want to show you this particular. Look at all these Fisher projections. I told you this would be sweet. What is this here?
Blurry.
These are your sugars, okay? Including glucose. These are shown with Fisher projection. Your carbohydrates have 1, 2, 3, 4. 4 chirocarbons. Okay? You'll see these in biochem. And all your different sugars are just stereoisomers. And they're drawn like this. But I also wanted to show you this. Your 1 carbon carbohydrate is this called glyceraldehyde. Well, 1 chirocarbon. When you have 2 chirocarbons, which is what we were doing, it's called erythrose or threose. Where have we seen those names? Yeah. In erythrose, the 2 OHs are on the same side. Because of that, other compounds where the main groups are on the same side are called erythro. It's analogous to erythrose. Threose has the 2 OHs on the opposite side. So that's where the erythro and threo come from. Because those 2 sugars there are diastereomers. We can also have things like this. Ribose and arabinose are C2 epimers. What does an epimer mean?
It just differs at one part.
Only differs at one side. You see? What's the difference in these 2? It only differs right there. The other 2 are the same. And that's called C2 because that's 1 and 2. And so we can now have terminology. These just differ at C2. They're called C2 epimers. There's some other things there. Basically, application of stuff. Showing you why these terms are important. You'll see that type of stuff in biochem. Back on the front, this may be the last thing we look at. No, we got to look at the stuff below. I'll do one below. You can do some more work on this page if you haven't already done it. Question. How might you separate the 2 enantiomers of this compound? Because that's chiral. And you can have the R form or the S form. How would you separate the 2? Because maybe you want to give this as a drug and the R form is good and the S form is toxic. If that's the case, you want to separate and only give the R form. How would you separate it? How are you separating things in lab?
Dissolving and then
How do you separate an impurity from your desired compound? Filtration, if the impurity is a solid and the other thing's dissolved. What's another way? Recrystallization. I mean, when you recrystallize, you're trying to separate impurities, which is one molecule, or maybe many, from another molecule, right? Can you recrystallize and separate enantiomers by recrystallization? They have the same exact physical properties. Do you think one is going to crystallize and the other not? No, why would they do that? They have the same exact properties. So how are you going to separate them? And lead to what? Okay. Well, it's very difficult. So let me show you how to do it. On back. Here's how you do it. One way. You can separate enantiomers using a chiral resolving agent. if you have a mixture of R and S, let's throw in another molecule. It's all S. Now you might say, well, how is it separated? Well, somebody did it somewhere. But since they did it, we can now use this. And if this bonds to this, this is two things. If S bonds to R, we get an SR. If S bonds to S, we get SS. So if we get those bonded, we now have this mix. Well, this mix is enantiomers. But what is this mix? RS and SS. That's now diastereomers. And diastereomers have different properties. And diastereomers can potentially be separated by recrystallization or distillation or something else. So now S could bond to these others covalently, but then you're going to modify your R and S, really modify it and make a different compound. It's more convenient to do a salt and get S to bond to these guys by an ionic and do just an acid-based salt, because acid-based salts can be reversed easily. You can go back. And here's an example of this. This amine is chiral, and thus it can be R and S, or D and L, or plus or minus. If you have a mix, you can react this with tartaric acid. And tartaric acid is naturally this, RR. By the way, where do you find tartaric acid? I think it's found in the kitchen. Isn't something in the kitchen tartaric acid? Tartrate? Cream of tartar? Yeah, that's where you find tartaric acid. And it's naturally RR because nature is miraculous. It produces RR. But then we can get that and use it. Now this is, what do we know about amines in terms of acid-base chemistry? They're bases. Now this is a carboxylic acid. It's actually a diacid. This is going to react to make a salt. Proton exchange, you'll get a plus and minus. But that's an ion pair, that's a salt. But that's R, RR. So one of them is RRR. Now they're not covalently bound, but it's still considered like they are, because they're ionically bound. The other one is SRR. And now what's the relationship between these two salts? Diastereomers. These have different properties, and actually, if you're lucky, they may crystallize. Maybe this one forms crystals, that one stays dissolved, you filter off the crystals, and now, how do you get back just the molecule? Well, you treat this with base and it'll take the H off, and you go back to there. It says it a little bit down below. There's also some discussion. It's also the experimental, the actual lab method for doing it. Okay? So making a diastereomeric salt, then you can separate your enantiomers. That's the most common way, or a common way. And the tartaric acid is called a chiral resolving agent. Okay? That's there. So on the back of the purple, let's try to finish up miscellaneous things. We just talked about G. One other thing you need to be aware of, moving into biochem, is there's a difference between capital DL and little dl. We're dealing with little dl. Big D and L means something different. Okay? You can read there. Alright? Now that will not be on any quiz or test. Alright? But that's just something important to know, the difference between little dl and big DL. They're both stereochemistry related, but they're different. Alright? I'll just put that in there because it routinely kind of comes up. Let's now sort of finish this by doing at least one on there, and you need to be doing the others. I might take a suggestion, I'm not sure. If you suggest the one I like, then I'll go with your suggestion. Anybody want to do a particular one of these? 3? Okay, I'll do 3. All right, let's do 3. Question, give the major product, show all stereoisomers formed. Is the product chiral? Is the product optically active? Show 3 and 4 good. Whoever shows 3 or 4. Fisher projection with phenyl 1 at top and phenyl 2 at bottom. Label product as erythro or trio. Okay, 3. First off, simple view. You got an alkene, double bonds in your benzene rings, we're doing no chemistry with those. Alkene, H2 with palladium, what are we doing to the alkene?
Three locations.
We're hydrogenated, adding an H to each particle, right? No? So if we don't do any stereochemistry, I mean, that's the product. New H here, new H here. In terms of predicted product without stereochemistry, it's easy, right? But all those questions up there really refer to stereochemistry. At this point, these are now tetrahedral. Are the two phenols going to be coming forward or back?
Back or forward.
That's kind of the question, but I'm not sure it's the exact question I'm going to ask. Let me start with this. How does H2 add? Are the two H's going to be on the same side or opposite? Same side. Because the alkene's walking down the road, the H is sitting on the metal, and boom, two H's come in. Let's show the two H's coming in on the same side. I would not suggest doing this. This is one of those times I told you that you would forget. How did I tell you to do this?
They're same, they're one and the same.
Start by turning this.
Oh, sorry. Yeah.
Yeah. Let's draw the alkene. The methyls are trans, okay? I'm going to draw one methyl like this and one methyl like this. Then the phenols, that's going to have to be like this, and that's phenyl 2, either way, and then here. Phenyl 1, that's just the starting material turn. But the two methyls are still trans there. Everybody with me? Okay? I suggest you just turn it. Just by turning it, we already have dashed and bold on the board and it's set. Now, when the reaction takes place, the pi bond ends up gone. And now we have an H here and an H here. Well, what is there? Now when I turned it, this became flat. Okay? Forward and back. Now, how did the H's come in? Same side or opposite? They either both are shot in from the bottom, or they're both shot in from the top. I'm going to shoot them in from the bottom. And so, there they are. And there's your product right there. This is with stereochemistry, where this was just very generic, and stereochemistry was not shown or accounted for. All right? I suggest you do it like this. To me, it's much easier.
On the test, if we did it where we folded the two H's, would you count that as correct?
As long as you answer the questions right, it's correct. You can do whatever you want as long as you get the question right.
How did you decide that the methyls were trans?
They're trans, right?
Oh, I mean, like,
Are they trans?
yeah.
What's the question?
Well, like, you went one forward and one back.
No?
Why?
I could have put this back in that. I just showed the relative stereochemistry, not the absolute. Do you agree that these methyls are trans? I mean, I drew it with the double bond in there. It's trans. Because, here, let me draw a trans methyl up, down. Okay? You see it? Methyl up, methyl down. Trans. Now, when I turn it flat, that's A is over here and B is over there. Now, when I turn it flat, tell me which way A comes. Coming towards you. And B goes which way? Goes back. So I just drew it as if I turned it. But I could have made that bold and that dashed. But that would have also been trans. That would have been the enantiomer. And we're going to get the enantiomer. We'll talk about that. But then I just add in the H's and it's done. So I'm suggesting you do it this way. Now, what's the question up there? Well, one of the questions is showing an Fisher projection. Well, here it is. Can you show that in a Fisher projection? Well, it's the same old thing, but some of the things you don't realize what we're doing, we just do it, okay? I want to look at this. I'm usually in the plane of the board, with something going away. The Fisher is going to be like this. Two things going away. And that's how I usually look at it. What can we look at going away? The things in the plane. Because usually the dashed and bold we say, is that on left or right? Did it say put phenol at top or what? Did it say?
Page one at the top, page two at the bottom.
Okay, phenol 1 at top, phenol 2 at bottom. Phenol 1 at top, so where's the ground? That's, the ground is here. I'm standing here on the ground, I'm looking down, kind of looking down through there. What's going away from me? If I'm up there, what's going away? Okay, hold on. I can get there by rotating. With the H going away, which side is phenol 1 on? It's coming towards you because it's bold, so it's on my left. With H going away, phenol 1's on the left. Thus, the methyl is on the right. Now I just need to bend my knees and look through here. With this H going away, phenol 2 is on my, it's dashed, so it's going to the hull. If I'm standing here, real light, right here, and something's going to the hull, it's on my, phenol 2 is on the right. Thus the methyl is over here. What's going away from me? There it is in a Fisher, but it's not how we were asked to draw it. Well, we can just rotate it like I showed you earlier. If you rotate phenol 1 to the top, where does this methyl go? Methyl over here, and the H turns down. And here, if you rotate the phenol 2 down, where's the H go? Here, and methyl here. And there it is with phenol 1 at top and bottom. There's your answer. Now we can say with phenol 1 at top and bottom, is it erythro or 3O? 3O, because your big groups are on opposite sides. Is the product chiral? Well, do you see a plane of symmetry? I mean, could you come through here? No, mirrors, M is mirroring H, that's not. Well, what about through here? Methyl mirroring H, no. Planes of symmetry are very simple in the Fisher. All you got to do is look there or there. There's not one. So since there's no plane of symmetry, is it chiral? Yes, it is.
Would you do the priority on that one, the phenol group?
No, we just look at groups on the side.
So it's the phenol would be C volume two.
This side, the priority group is methyl.
No, for doing just only RS.
Oh, here?
Yes.
So R and S. We'd have to take a little time, perhaps. No, maybe not. I don't know if I can do it quick. Try it on your own. H is obviously 4. Carbon with just H is 3. This is a carbon with carbon H. That's a carbon bind to all carbons, so that's going to win. So that's 1. This is 2 this way. 1, 2, 3 clockwise, but the H is coming forward, so it's S. Yeah. Okay, what were other questions? Is the product optically active? These 2 questions here really need some clarification. That molecule is optically active because it's carbon. But we also get another molecule. How could this have been different over here?
They just tagged the top.
We could have gotten the 2 H's from the top. And the 2 H's came in from the top. Nothing else would change. We would have just erased our pi bond and put the H's at the top. And these are actually enantiomers. To really see their enantiomers, you'd have to draw this in a fissure, and you'd have to rotate it. If you rotated it, it would mirror what we have over there. You can also see its enantiomers by doing R and S real quick. Let me do it real quick for you. This is, we've already done that, that's S. This is, that's 1, 2, 3. It's really easier to do it here. It's easier to do it in the fissure. Carbon with all carbons is 1. Carbon with carbon H is 2. Methyl's 3. Clockwise, but the H is coming forward. So what is this?
Yes.
S. They're both S. Okay? Both S. You have to check yourself, but I guarantee you, I bet you $100 gazillion that these are R. Okay? Check yourself. Okay? You get enantiomers because the hydrogen can attack from either side, and that leads to enantiomers. Okay? You can see it. You believe me? Question.
On the exam, would you allow us to draw all the carbons, I guess, in the plane, and then just draw the hydrogens in perspective? Instead,
I'm not quite following your question. Here's the answer. You're asked to draw this, so you need to draw that there.
okay.
You're asking how to get here?
No. I'm saying because it's easier for me to draw a Fisher projection from how we usually draw molecules.
Again, I don't,
Okay.
I'm not concerned with how you get the right answer. If you get the right answer a different way, then more power to you. I'm just showing you the way I do it. Ultimately, you got to show this. If you can get to this point some other way, then great.
So when it says show the all stereoisomers for the actual product, when we're drawing the product itself, before the Fisher projections, you want the enantiomer.
Where did it ask that at?
The very first, the original question.
Where at?
It's like the original question. For the major product performance reaction, show all stereoisomers formed for the major product.
Okay, well, that's it. That's them two. That's these two. A lot of times, you'll just show this and you'll say plus enantiomer. We did that coming through our reactions. Not plus enantiomer. Well, that's the enantiomer. And let's say this to kind of finish up this. Please work the other three there. Did we answer everything? Oh, is the product optically active? That question is a little bit vague. The answer is no. Why is it no?
Because it's received.
Because it's going to be a 50-50. Individual products are optically active, but the 50-50 mix is not. So you really kind of have to ask me to clarify. Are you talking about individual or, okay. So that question is a little bit kind of fuzzy. But the 50-50 mix is not. Now here's what we need to say to sum this up. There's a summation on the back. F. All right, you can look back at this. None of the reactions we're doing right now are enantioselective. That is, none of the reactions we're doing right now only give one enantiomer. If enantiomers are possible, the reaction is going to give both. Okay? And if you look back at the reactions we did 2 days ago, most of them I said plus enantiomer. How do you get both? Because whenever the alkene attacks, you can attack either side. Okay? Epoxidation, the oxygen is over here. Alkene attacks it. You end up with a bond that way. But the reagent can also be over here, and you end up with a bond that way, and it's 50-50. Okay? All the reactions we do, we're going to get both enantiomers. We say it's not enantioselective. It doesn't select for one over the other. But many of our reactions are regioselective, right? Yeah, most of them are regioselective. That's a different term, but they're not enantioselective. Why? One reason is they can't be. Look at this reaction. They can't be because of this statement. You cannot create optical activity out of the blue. Is this optically active? Only if it's chiral. Is that chiral? Not chiral. Not optically active. Okay? Is this optically active? No. Well, guess what? You can't make something that is. And why is what we made not? Because it's 50-50. If you do this reaction and just get one, and it's optically active, you have a Nobel Prize. All right? But it ain't going to happen. So that's a statement. Optical activity cannot be just created fresh. It has to be handed down. And a lot of time chemists just argue, where did optical activity begin? Okay? So none of the reactions are going to be, everything's going to give enantiomers when enantiomers are possible. Please do the other three. I want to move on. There may be something we're forgetting, but I think that's about it for stereochemistry and alkene reactions. We need to move on to our next and last topic for test 2, and that's alkyne chemistry. Carbon-carbon triple bond. Now, the carbon-carbon triple bond has 2 pi bonds. And the reactions are going to be very analogous. It's just when you have 2 pi bonds, it's twice the fun.
Twice the reactions.
Okay? There'll be some slight differences. But we're going to react with HBr, and we're going to put cation on the best carbon. Okay? So here's a handout. You're all going to pink sheet today. Let's cut it in half so we can get them out quicker. While they're being passed out, some of you did bromination yesterday. When you took melting point, did the white solid turn color? What did it do? Brownish orange? So you had an alkene, these are phenols. reacted with bromine, and you made something like this, stereochemistry. What was going on when the compound melted? When it melted, it was reversing. It was eliminating Br2. Going backwards. And what color is Br2? Brown orange. Yeah. Why does it go backwards with heat? Because heat magnifies what term? Entropy. One molecule going to two. The reverse is entropy driven. And how do you drive entropy? Heat. Okay? It was reverses as it melts. Once it becomes liquid, then all the chemistry can take place. So as it becomes liquid, it also does this. In the solid state, it's harder for the chemistry to happen. Okay, everybody got a handout? Summary of alkynes here. Terminal alkyne. Don't lose track of your two carbons. HX. We can add HX across the pi bond and get this. Why does the X end up on that carbon? All right, because this is linear, you guys often kind of lose the carbons here. All right, all that's linear. But when we make cation here, we're going to leave it on left or right. Left, more substitute. Okay? So we're going to make cation over here, and then the Br attacks cation. That's how you get the Br over here. That's linear because it's SP. Now it's SP2, so it's triple planar. So don't forget your basic geometries and stuff. Okay? I'm assuming you're handling that.
Is that H normally written in on the original alkyne?
I do on terminal alkynes. I write my H's in on terminal alkynes. I also write it in on aldehydes. So it's kind of naked without it. Doesn't have to be. Over here, there's a drug with an alkyne. That's not terminal. It's got a methyl on it. There's an example of a drug with an alkyne for diabetes. So we'll react with HX. You can look back at this summary. We're basically reacting with pi bond. With an alkene reacts with hydrogen, the pi bond's reacting. The pi bond reacts. The only thing is you're just left with a pi bond because there was two to start with. Well, that can react again because we know that alkenes react, so it can react twice the fun. All right? This is just a summary review. So HX or X2 will do that. We can also hydrate the alkyne, react it with water. Here's our hydroboration. We know how that reacts. Pi bond attacks boron, then it throws the H. Okay? It's the same mechanistic stuff, it's just you have two pi bonds. We can react with hydronium ion, water, and acid. With alkynes, you typically include a mercury catalyst. Talk about that. It's not absolutely required, but it's historically required, and you'll see it in the textbook. Actually, in lab, you're going to hydrate an alkyne, but you're not going to use mercury. It's a little toxic. You've developed a hydration that doesn't need mercury. Now, when you hydrate the alkyne, let's look at it. Mechanism, this is H+. So this will attack H+, leave a cation, which carbon, left or right? Left. Water will attack, we'll have an oxygen bonded there, and then the oxygen will lose an H. Okay? All you got is just an extra pi bond. If that extra pi bond wasn't there, you'd make that. Well, it's just got a pi bond still there because we only used one. Well, this is special. This is called an enol. You'll see enols in organic too. Enol comes from the fact that it has an alkene with an OH on it. And those are usually alls, alcohols. There's an enol. Also, that's what a donkey says. Enol, or something like that. Something like that. Something stupid to remember it, right? Enols actually undergo a process called tautomerization. That'll be new for us. But the mechanism will be quite doable. And the enol and the ketone are isomers in the same formula. Tautomerization leads to the double bond moving here, and the H being here. As CH2 is now CH3. So we'll see the process called tautomerization. We may also have an Oreo cookie. Okay. Basically, that's just a little bit of an overview. The main thing is this should be very similar to alkenes. There's some drugs with alkynes. So let's get started. Chapter 11, some in chapter 12. Let's do some nomenclature real quick. Hopefully this pink shows up. It looks a little dull, dim. Okay, nomenclature. Just with alkenes, except the ending is going to be -ine, Y-N-E. With IR, we mentioned terminal alkynes versus internal. So that's one thing. Let's name these two alkynes. What's the longest continuous chain? Well, it's just one chain. 1, 2, 3, 4, 5. So it's not pentane, but pentyne. Well, if that's pentyne, what is this? Just like with alkenes, you have to say where the double or the triple bond is. Where is it here? 1, 2. The triple bond's at the 1 position. That's 1 pentyne. See the similar to alkene? What do you want to call this? Two pentyne. Constitutional isomer. How about the one on the right? I heard it. 3 heptyne. 3 heptyne? What if we put a chlorine here and we gave it a little stereochemistry? What would that be? Not 2-chloro. Why do you say 2-chloro? What's the way? 6-chloro. Because functional group gets priority. See, if that's 2, the functional group would be 4. Right? But since I showed some stereochemistry, we need to be more clear. What is that? You got it? Yeah, it looks like R. So we can put an R here, stereochemical descriptor, because there could also be an S version. Okay, let's look at electrophilic additions. Electrophiles adding. You know, I don't like the term electrophiles adding, because it makes it sound like the H plus is doing something. I don't like that terminology, but that's just the way it's stated. I'd rather focus on the pi bond. The pi bond is doing something. The pi bond's attacking. All right? I think it's unfortunate terminology. All right, if you have an alkyne, ACl, it'll react. Pi bond will break away. Are we going to leave plus on left or right? Left. These break away this way. Triple bond, I don't have 3 arms, but pretend there's 3 here. One of them breaks away, makes a bond to H, leaving a double. Correct? And so we get double. Now I'm going to draw this like this, so you can see here. Now 2 H's on the end. I'm going to draw that trigonal planar, because it's now trigonal planar. What's here now? It's a plus charge. That's a plus charge on an alkene carbon. It looks odd. That's actually pretty bad. Because what's the hybridization of this? SP, double bond region, single bond region. SP, linear, that's why I drew it linear. An SP cation is not as good as an SP2. We're going to show it anyway. How do you get final product? Or it's that product. This attacks here, and you get that product. Chlorine now bonding to the same carbon as the propyl. It's just upside down, right? I could have drawn it like this. Is there any difference in those two? There's no difference in those. But this can react again because that's an alkene. And we know alkenes can react with ACl. We would get that, right? If I didn't show you the product, I would hope you could predict it. You should be able to. Because this reacts with H+. When it reacts, are we going to leave plus on left or right? Left. So this hinges away that way, and we get UH added, chlorine there, and there's a plus there. We need to talk about that, because you see the donation here. Is the chlorine going to help that cation or hurt it or what? This is actually a conundrum. Chlorine has lone pairs. What can we do here? Back bond, but it's going to be called something else. It's sort of like that. That's a good term. That's going to lead us to double bond to chlorine. Now the chlorine has a plus charge. There's a new H here. What do you call these two? All we did was move pi electrons. We didn't make a sigma bond. When the chloronium back bonds, you make a sigma bond. Whenever you make a sigma bond, you're making a new compound. Here we just made a pi bond. We didn't move any atoms. What is the relationship between these two? Starts with an R.
Resonance structures.
These are resonance structures. What's the hybridization of the chlorine? sp2. One of the lone pairs is in the p orbital. Why? Because there's a p orbital here. And the lone pair that's in the p orbital, what's it busy doing? Interacting with that p orbital. It's doing it. We can't see it here. We see it fully here. True structure somewhere in between. The chlorine is interacting, but it's like, I don't want to interact too much because I don't want to be too positive. We do resonance arrow, double-headed resonance arrow. This is a resonance stabilized cation. That's another reason we get that cation. You already predicted it before we did that. How do we get the final product? Cl minus. That's here. That gives final product. We end up with 2 chlorines on the carbon. Called a geminal dihalide. What does geminal mean? Twin. That's when the groups are on the same carbon. They're like twins. If they're on adjacent carbons, we call them vicinal. They're in the same vicinity, but they're not twins. Bromination of an alkene gives a vicinal dihalide. There's no stereochemistry here because that's not chiral. So there's nothing to show other than the regiochemical outcome. Questions about this? It reacts twice. We could show a reaction that just did this. You just take 2 equivalents of ACl and go directly there. So it reacts twice. It can be hard to stop here, but that's the chemistry. Any questions about that? What do we see new there? The resonance structure was semi-new. Again, we'll keep seeing that come up a good bit. What else was really new here? What's new? This is resonance. We did this before. We had an oxygen before. Let's go back and let me show it to you. It was one alkene reaction set. Yeah. Right down here. Remember this? This is on the alkene white set, back in the first page. Which was formed. Question was, where did we make cation? Why did we make cation down here? Everybody got that? Looking back at the notes, why did we make cation down there? Because of resonance. Why do we make cation here? Resonance. Also because of induction, but there's 2 reasons. I want to point out the resonance there. Big thing. Resonance is a big thing.
Professor, if you ask us to draw the stepwise mechanism, do we need to draw the resonance?
Do you need to draw the resonance? I don't reckon you
process?
need to unless it says to draw all resonance structures. Again, what is resonance? Resonance is an alternative Lewis structure. We could have done resonance on day 1. For example, this needs another bond. Well, if we're out of valence electrons, how can we get another bond here?
Take it from
We can ask this guy to share. And that's how we make like double bonds. Well, you get a double bond, but it's not yet neutral. You just have charge. So, I mean, we could have did that on day 1. Resonance is an alternative Lewis structure. The charge is delocalized. Because in the hybrid, some of the positive is on the carbon, but some of it's on the chlorine. Okay, let's look down here. Reaction with X2, like bromine. Usually chlorine, bromine. Iodine works sometimes. Chlorine's a bit too dangerous. Kind of a crude joke, you can always tell, you go to a chemistry conference, you can tell when you meet a fluorine chemist, he or she will be the one without thumbs. Not even funny. Because they, explosive. Actually, a chemist at Clemson, he retired in the past 5 years, but fluorine chemist. All of his career, including graduate school, but he's missing an arm and a couple of fingers. Dr. DeMarteau at Clemson. But I had the privilege of knowing him Had an accident when he was in graduate school for fluorine. Telling me some stories one day at lunch. They just have a tank of fluorine outside back in the 60s, just like natural gas, you know, like a tank sitting out there, the line pumping into the lab, fluorine. He said today that that would never be allowed. Okay. What we got here? We got a pi bond and bromine. We know pi bond reacts with bromine, right? Let's see. That bromine is polarizable. It gets kind of, you know, they get mad at each other. This can attack. Are we going to leave plus on left or right?
It's going
We can do this. Don't lose track of carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And H. There's now a Br on this carbon and a plus here.
whatever.
Be over
that-
at
that's
that,
fine.
But we only use one pi bond. There should be a double bond remaining. Now, is this going to do anything?
Exact bond.
Yeah, we learned this on back bond. Now, I think Dr. Rydell showed the back bonding in lab kind of all at the same time. And didn't really show this, because I'm really the only one that does NAL. If it back bonds, we get. Actually, this is planar right here. When it back bonds, it's going to push that through one way or the other. It's here. And if you think about it, that is very ugly bond angle there. Because even when we usually make it, it's a regular bromonium, what's the bond angle? 60. That's 60. But what does this want to be usually? 109.5, because that's tetrahedral. This wants to be
120.
120. You're asking it to do 60 degrees tighter than it wants to be. This one, you're only asking it to do 49 degrees tighter than it wants to be. That's really bad. Some chemists actually argue that this may not actually form. Even that may not actually form. We're not going to go there, but in terms of our standard mechanism, we can do back bonding. Then the other Br minus will attack where?
Backside.
Left or right? Left. More substituted. Kick that off. What do we get?
Trans.
We get what's shown. Why are the bromines trans or E? Well, right here. Because if this bonds down, it's from the backside attack. That's why this is E and not Z. So your mechanistic thought predicts your stereochemistry.
So if they say it's not formed, it's still always formed the trans one?
Great question. And so you got to reconcile that. I'm just telling you that that's ugly. You agree that's uglier than this? So we got some, okay, we don't have time to get into too much. Now we have a double bond. Double bonds react with bromine. What do you get? Bromine added to each carbon, you get this. Here there's no stereochemistry because neither are chiral. You don't have a double bond, and so there's nothing to show there in terms of D or Z or cis or trans.
And for the second reaction, does it back bond or does the stereochemistry say that?
Here?
For the second half of this?
Yeah, that back bond is just like any alkene. Yeah. And then it comes in the backside. But because the product is not chiral, it doesn't matter how you show it. Because there's not two different ways. Next page, we look at hydration of an alkyne. Please look at that, including particularly the tautomerization. Please be doing some reading about tautomerization. That mechanism, which is pretty simple. And then look ahead to the remainder of this handout, okay? Really, according to the syllabus, tomorrow's our last day before test 3, before test 2. Friday, new material. Test on Monday. Please come prepared tomorrow.